Okay, good morning, everybody. So our morning session start with the continuations of the Alexis talk with about classical and quantum Bollinger models.
Thank you for being here. Now, this is a surprise. Apparently, my voice didn't like my yesterday's lecture and decided to go on strike. So this is going to be interesting. That's how you're going to hear me for the rest of this talk. It's probably good because I will be tempted to talk less and probably don't give you so many details. So I just remind you that yesterday we were quantizing the Hermitian matrix model. It's just n-square harmonic oscillators, so in principle its quantization is trivial. However, it has to be done in a way that the constraint that the angular momentum has a fixed value be easily implemented and the connection to the particle system be made in an easy way. So to that goal, we defined the analogs of creation and annihilation operators for the matrix. So these are matrices. They commute in the standard way that you would expect them, only matrix element by matrix element. And we defined the two possible definitions of what would be the Hamiltonian, AA dagger and A dagger A. Now, these are genuinely different operators because of the matrix ordering. This is like a left Hamiltonian, that's like a right Hamiltonian. And we found that the commutation relations of those matrix operators are of this form, and that this form actually is the UN or SUN, but UN in this case, algebra in disguise. If you expand these matrices in the appropriate basis, the elements satisfy the UN algebra. And that's kind of a convenient way to write the algebra because it doesn't involve any explicit structure constants. They are introduced once you choose the basis, but they don't need it in this form. I remind you, 1 and 2 are indices of two different spaces on which these matrices act. That's a convenient packaging of the matrix element commutation relations. So that's where we left it yesterday. Since these L and R are UN algebras, they have Casimirs, and it's no surprise that the Casimirs of the UN algebras they represent are just the traces of their powers. The trace of L to the first would be the U1 charge, L squared would be the C2, the quadratic Casimir, and so on and so forth, or at least related to those Casimirs conventionally defined. So, without going into the details, you can show that these quantities commute as quantum operators, the scalar quantities, and therefore they are quantum integrals of the system. The second one of them is essentially the Hamiltonian, because it's the trace of AA dagger, and that turns out to be the Hamiltonian. So the Hamiltonian is one of those conserved quantities, so these quantities are also conserved in time. Those traces for the left and right Hamiltonian matrices are of course related, because once you take a trace, then you can rearrange the matrices. The price you have to pay is some quantum reordering, but that amounts to just a constant. So you can use only one of them and expand and express the full tower of INs in that basis. This is also a quick and dirty, if you wish, proof of their commutation. Since L and R commute, as we showed in the previous slide, the IN defined from L and the corresponding IN tilde, if you wish, defined from R will definitely commute among each other, and yet they are related to each other. One is just a rewriting of the other. So all these things have to commute. You don't have to work any harder than that. That is the Hamiltonian. It's proportional, in this case, to L1, actually, because it's already, L is already quadratic in the A's. And also, that Hamiltonian obeys these commutation relations, which means that these matrices act as creation operators. Each matrix element is a creation operator. Those are the n-square creation operators that we talked before. Yes? Right, yes, let's go to the definition. L is The A is like a matrix creation operator, exactly what you would write for particles, but with matrix coordinate M and matrix momentum P. So A is the annihilation and A dagger the creation operator, and A dagger A, which is still a matrix, is something that would correspond to the Hamiltonian of a particle. So it's a matrix Hamiltonian. And so is A dagger, quantum ordered.
And what was the relation between this P and M and the original variables?
M is the coordinate, and P is the corresponding momentum to that coordinate. P is the canonical momentum. P is m dot in terms of equations of motion. It's the standard conjugate momentum of the variables m. M is a matrix, it's n square variables, and there are correspondingly n square momenta, and that's the matrix P. And again, their commutational relations are of this form, or of this form, if you wish. Each matrix element of n with each matrix element of P commutes like that, and that is written conveniently in that form, involving that operator that I wrote.
Thank you. Thank you.
I know it's a little bit dense, but I want to introduce notation that will make my life a little bit easier. So here we are. Now we have obtained the quantization. It was trivial to start with, but now we have to implement the conservation of the angular momentum. We need to weed out all the other states and only keep the states that belong to a particular value, in quotation marks, of this angular momentum that represents unitary rotations of the matrix, which, as we argued, is the thing that will fix the eigenvalues to be of Calogero type. Now, that classically was just a Hermitian traceless matrix. Quantum mechanically, it becomes this commutator n ordered, and that turns out to be simply the sum of left plus right matrices R. So it is also UN algebra, because remember, L and R are UN algebras and they commute. So this is the direct sum of those algebras, with the constraint that the trace is 0, so the U1 charge of that algebra is 0. So fixing the value of J in the quantum mechanical case means fix a representation of that J, of the SUN actually, obeyed by that J, it's S because of that relation. And then identify the states that are related through J as a unique physical state. They are gauge copies of each other. Remember that this J is what generalized the particle permutation when you consider the particles as the eigenvalues of a matrix. So I won't go through too many details, just to give you the flavor of it. When you write the matrix elements of A, you see that this summation over this intermediate index, this is the matrix multiplication, amounts to summation of n operators, and lo and behold, each one of those operators, no summation on S, just an operator that depends on S, J, and K, each one of those operators is a UN algebra. It still satisfies the UN commutation relations. So L is a sum of S such UN algebras. L was itself a UN algebra. Now it becomes a sum of smaller, if you wish, or individual mutually commuting UN algebras, as we see here. And that is convenient because then J becomes the sum of all these UN algebras for L and R. But these are very special realizations of these algebras. If you look at each one of them, say LSJ, which is this, if you look at it, it's nothing but the annihilation operator, ordinary annihilation operator ASK times the creation operator A dagger JS. So since S is fixed, this is the conjugate of that when K is equal S. And I'm saying all that to tell you that this is actually the Jordan-Schwinger realization of the UN algebra in terms of bosonic operators. Now, if you're familiar with the Schwinger-Jordan, or Jordan-Schwinger, I should say, realization, it tells you that if you take the representation matrices of any group, see that as a matrix, and multiply them to the right with a vector of annihilation operators and to the left with a vector of creation operators, that quantum mechanical object, which is now like this matrix sandwich between these two vectors, so it's a scalar operator but it's quantum mechanical, those quantum mechanical operators obey the algebra of the representation that you started. So this is a realization of that UN algebra in terms of those operators, but that realization does not give you all the representations. Because these are bosonic operators, it gives you only the fully symmetric representations. That means, each one of those LSs has the representations that correspond. In its Hilbert space on which it acts, it has the representations each LS has. The singlet, of course, when it acts on the vacuum, the fundamental, the doubly symmetric, the triply symmetric, and so on and so forth. These are the only representations that are in each one. In each one of those LSs. Of course, the direct sum of those, the sum of those LSs will be the direct sum of some representation here from some representation from the same group. And since you have n of them, they contain all the representations. So each one of them only symmetric, the sum of them, the full content with various multiplicities, each one. A couple of more facts are relevant so that we decide what's happening with J. So this is all the representations of SUN. This is again all the representations, but because the Casimirs of LS and LR are related, these two representations are conjugate to each other. That means that J, which is the sum of them, will contain irreducible representations only of the form R times its complex, its conjugate representation. So for such representations, which is all there is into J, the U1 charge is 0. We knew that because J has no U1 charge. But also the Zn charge is 0 because if you multiply a representation with its conjugate, the total number of boxes is a multiple of n. Therefore, we derive the important, for our purposes, fact that the Young tableau of the representations in which this operator decomposes have vanishing Zn charge, and therefore the number of boxes are a multiple of n. So we must construct states of our n-square oscillators that obey this constraint. And again, I will give you a flavor of the construction. You start from a vacuum annihilated by all n-square harmonic oscillators, and then the generic state, which is an eigenstate of the Hamiltonian, will be that vacuum with a string of creation operators applying, and this creation operator could be any matrix element of these matrices A dagger. Each and every one of them is a creation operator. Of course, that's not the kind of state that we want, because these states have to transform in a specific representation of J. But we see that this state has several indices here. All the right indices, it turns out, they transform like the fundamental of the R representation. That's what R does. It rotates, it mixes this R, these left-right indices, and all the left indices, J indices, transformed in the fundamental of the L. So all these states, for a fixed number of these operators, the set of these states transform in this total representation, the product of n, little n fundamentals for L and little n anti-fundamentals for R. So now we need to take this representation and perform the Clebsch-Gordon decomposition into irreducibles of J and keep the J that we want. So let's see. Remember that classically, I hope you remember that classically, if you choose J equals 0, you get free particles. And to get Calogero particles, you have to get to choose the next less trivial form of J, which is rank 1, the diagonal minus the trace. And that corresponds in actually choosing a fully symmetric representation. I will justify that a little bit later, but fully symmetric representations are fixed by a single Casimir, and that's exactly the statement that they are rank 1. So we have to do that Clebsch-Gordon decomposition. That sounds complicated, but we will use a trick. We will take this operator J, the matrix element Jk, and put it equal to this form, where psi's are another set of auxiliary creation operators. They are not part of the original system. I just introduced them for convenience. You will see why. This realization now of UN, because this is again a Jordan-Schwenker realization of UN, is by construction only symmetric. It contains, again, these boxes, so that's why I chose it. And further, because, and now I say that I want the full representation J plus that to be a singlet. That is, if I put J equal to this, it's tantamount to saying that the original J plus the representation created by these guys is a singlet. The fact that it's traceless fixes this condition. Where am I? the fact that it's traceless fixes this condition, that the total particle number of these oscillators must be L times N. So that fixes this representation to have L times N boxes. And therefore, if you take the state that consists, all right, yeah, if you take the state that the states that we created before and augment them with these operators and demand that the full thing is a singlet, you end up building this state. Again, the way that you do it is that you now have the freedom to multiply the vacuum with these creation operators. You need to contract all the indices to make a singlet, but the only way that you contract the indices of these hanging psi's is through the fully antisymmetric tensor of SUN. So this is the only invariant that you can form if you have your matrices A and psi. You can verify that. There's no other way to contract the indices. Because you want to have that many operators applying on the vacuum, you have to raise that to the Lth power. And now you're done. This is a state, the lowest state, that would satisfy the constraint that the representation of J is rank 1 with Ln boxes. And that you can multiply with any traceless operator, which is a singlet. So this is the generic form of that state. You take the creation operator matrix, raise it to a power, take the trace, and multiply with as many factors of that as you want. So this is our states. They are eigenstates of the Hamiltonian. You just count the total number of creation operators, A dagger, and they obey the constraint that J is in that rank 1 L times N fully symmetric representation. The energy is the total number of creation operators, and it turns out to be like that. This is the factor that you get because of this determinant essentially here. This is the 0-point energy of the n-square oscillators, and this is the excitation energy. And we recognize that up to this shift of the ground state as being essentially the energy of n, not n-square, n bosons, or independently of n fermions. And that's essentially bosonization. The expression that I give you is the bosonized form in the field theory sense of n fermions or n bosons. Let me explain that a little bit. If you have a harmonic oscillator in which you put bosons, the ground state, of course, is when they are all on the same ground state, which is excitation 0. Now you start building excitations. So if excitations would be to take a few of those particles and put them in higher states. And of course, the total energy would be the occupation number of each oscillator single body state times the energy. So that would be one way of expressing the energy. Another way of expressing the energy is to say the following. I will start from the topmost particle and I will ask, what is its excitation with respect to the ground state? I imagine that I built the state by pulling these particles up. So this one I will call M1. This distance I will call M1. The next one I will call M2. The next one I will call M3, and so on and so forth until I have everything, and everything else here would be 0. Now these M's by construction are such that M1 is bigger or equal than M2 is bigger or equal than M3, and so on. Because the way that I've done it, I start with the top particle, and that has the highest M1, so everything else will have the same or less. Otherwise, I'm double counting. And now, if you ask, what is the energy? Well, the energy will be the sum of these numbers. And there is And yet another way of doing the same thing that I don't want to overdo it. You say that, let's see, I have here excited 3 particles. I could imagine of exciting. That's standard bosonization, by the way, but I thought it might be interesting to repeat it for the purposes of what we are doing here. I will take these particles. I see how many do I excite. I excite 3 particles here. So I will start with these 3 particles, and I will excite them all to the lowest excitation level. So here I am. I start with these 3 particles, and I put them all here. 1, 2, 3. And I will call that, well, I called it already M. That's not my M, so sorry about that. I will call it N. That's N1. Then I say I will take the remaining particles and I will excite them to the, I will keep one there and I will take the remaining particles and excite them to the next energy level. In this case, it's the same. So N2 would be 0 here. And finally, I will take the remaining particle and I will excite it to the, to the level that it is, and that would be N3. Again, N1, N2, and 3 fully characterize, fully specify what state I have. I hope that this is visible. And now they don't have to obey any relation because each one of them is independent. N1 was 3, and 2 was 0, and 3 was 1, etc. What is the energy that they produce? The lower one raises all the particles that I have excited. So it will be 3 times N1. The other one raises the remaining, which are 2. So it would be 2 times N2. And the last one would raise only 1 particle, so 1 times N3. So it would be, if I had labeled them differently, if that was N1, if that's still N2, and that's N3, it would be 1 times N1 plus 2 times N2 plus 3 times N3, and so on if I had excited more, with now these N numbers obeying no relation among each other. That's exactly what I have here. These numbers, Mk, represent these excitations. And I guess that is a mistake because I should have taken into account this N here. So I'm sorry, this is wrong. I will correct it in the post. So this is K times Mk, because you see that here I have N of them. This N is K raised to the Mk, so it's K times Mk. So I have exactly what I described here with K and K plus a constant. So I'm telling you all that to tell you that this is exactly the energy levels of N non-interacting bosons in a harmonic oscillator with this extra shift on their ground state. Or this, if you wish, because they would have a shift of N over 2. Exactly the same game can be played with fermions. And I could show you that, but I'll do it later. And the fact that the exact same description is valid for both bosons and fermions is bosonization in one dimension, because this is a equally spaced, relativistic, sometimes we say spectrum in one dimension, a chiral one. Okay, so now we have our energy. We can recast the energy in terms of bosonic quantum numbers. These bosonic quantum numbers are essentially the ones that I defined here versus the ones I defined there, and they have this expression. These bosonic quantum numbers are obtained this way, and now they satisfy some bosonic relations. And finally, I was pointing to the wrong thing, I think. And finally, you can, to absorb, so that's how you go from here to here, these ends in terms of m's I didn't define, but you still have this shift. And because you would like to make things look as much like harmonic oscillators as possible, you define some new numbers, n bar, that we can call the pseudo-excitation number. They're simply the n's plus this extra shift, and that extra shift, which depends on which I you have, accounts for this extra ground state energy shift. So now the spectrum fully became the spectrum of free and non-interacting bosons in a harmonic trap. It's just that these excitation numbers, pseudo-excitations, now obey this relation, which tells you that they obey some kind of exclusion statistics. They cannot be equal they have to be at least L units apart. And I know that in principle L could be fractional, but remember, in our case, L was an integer, because in our case, L times n is the number of boxes in the Young tableau in the representation of J. So here, everything works exactly on an integral lattice as I showed you last time. Okay. So this is the quantization of the Hermitian matrix model, and I would like to conclude with some parting remarks for this model. One question is that I gave you the spectrum, and I claimed that this will be the spectrum of Calogero particles, but where is this quantum mechanical Calogero system? I argued that classically, the system would reduce for the proper choice of J to the Calogero particles, but it would be nice to see it quantum mechanically, and in particular, to identify the coupling constant G, the strength of the inverse square potential, with what I have done here. Well, this can all be done and will be done. I save it for the unitary matrix model simply to share the goods between the two models so that I don't do everything for one and give short shrift to the other. But once you do it, not surprisingly, you see that the coefficient of that interaction term, this G, becomes simply the quadratic Casimir of the representation of J, which in some divided by n, which in this case is L times L plus 1. I remind you that the quadratic Casimir, if this number of boxes is, I don't know, call it K, the quadratic Casimir of this representation is K times K plus N, right? For where this N is for N minus 1, actually. So for SU2, sorry, that's a better way of writing it. For SU2, when N is 2, this would be K over 2 times K over 2 plus 1, which is the standard J times J plus 1. But when you have SU3, etc., you have to put N there. So when K is itself L times N, N pulls out, and you get L times L plus 1, and this total factor of N squared drops out because of the way that it appears in strength. I will show you that, but I wanted just to give you an idea why it is like that. We will talk more about that. But before we go further, we have one puzzle. I argued that L here is an integer, but why does it have to be an integer? Well, because of group theory, because L is related to group theory. It has to do with representations, etc. Yes, but why? In the particle system, there is nothing going wrong if you choose L to be fractional. Why does the matrix model insist that L be an integer? Well, remember what we did was from the particle model, and then we embedded it in a matrix, in this way augmenting the permutation symmetry of coordinates and of particles into the full UN symmetry. When you augment a symmetry and then you realize it on a Hilbert space, you run the risk of facing a theory that has anomalies. And that's exactly what happens here. This realization would be anomalous if we chose L to be fractional. So this L is quantized in exactly the same way, physically and mathematically, as the monopole number has to be quantization. You have probably seen an alternative derivation of the fact that the monopole, the magnetic monopole number, must be quantized in terms of embedding it in an SU2 group, and then the quantization is simply the quantization of the Casimir of the angular momentum of the group. That's exactly what happens here. We have a monopole-like quantization that is not needed by particles, but it is needed when you embed them in matrices. Also, remember that before I was arguing that G can be parameterized as L times L minus 1. Here it is L times L plus 1. So this L that appears in the matrix model is related to the L that I was talking before this way. And this L is an integer, 0, 1, 2, 3, etc. So the L bar that I argued before fixes the statistics is 1, 2, 3, etc. The value L equals 0, other than the fact that we have no fractional values, the value L equals 0 is missing. And I argue that L equals 0 would be 3 bosons. L equal 1 would be 3 fermions, and L bigger than 1 would be kind of super fermions, further excluding each other. So, I'm sorry?
then does this anomaly show up in some way?
Oh, absolutely, because first of all, I'm talking about a Hermitian model. There are no boundary conditions. It's a fine.
Right. So, but if you kind of think of a finite system,
Because this anomaly has to do with the angular degrees of freedom and how they are realized, it has nothing to do with any conditions that you impose on the matrix. These conditions would still need to be U conjugation invariant, otherwise you would be breaking the basic symmetry, and that conjugation invariance would still be realized in the same way. So this is very generic in the matrix model. You cannot avoid it. So still, where are the bosons? And the answer is they're gone. The matrix model does not reproduce bosons. You're probably familiar with the fact that matrix model naturally fermionizes its eigenvalues. So even the matrix model in the invariant sector, where the angular degrees of freedom are in the L equals 0 representation, still represents free fermions and not free bosons. And sometimes we say that quantum mechanically this L is renormalized to L plus 1. So what would be bosons? They become fermions. Okay, let's move on to the unitary matrix model. Wait, why unitary matrix model? Remember that we are embedding particle coordinates into eigenvalues of a matrix. What if these particles now have to lie on a periodic space, so they are, say, on the circle, so they must obey some kind of periodicity condition? You could say, I will take my model and impose periodicity on the eigenvalues. That's an extremely awkward operation. You really want a matrix model that naturally includes this periodicity in its own eigenvalues. Lo and behold, that's the unitary matrix, because the eigenvalues are pure phases, and phases live on a circle. So U will be a unitary matrix. U n by n will be our fundamental variable. The eigenvalues of U are e to the I x n, and this x n will be our coordinates. And the Lagrangian would be exactly the same as the Lagrangian of a free particle when it's written as the exponential of something. If you were e to the ix, that here would simply be, with an I, would be x dots. So this would be x dot square, the kinetic term. So this Lagrangian would be the free kinetic term of a particle. It is actually the kinetic term of a particle moving, if you wish, of this unitary matrix point moving on this UN space. And the equations of motion immediately when you vary with respect to U are that the time derivative of this matrix, or the other way around, it turns out you can put U minus 1 wherever you want, is 0. Although you might think that dealing with unitary matrices would be harder than dealing with Hermitian matrices, in fact, everything is simpler. First of all, this model has more invariance than the Hermitian matrix model, because you can independently multiply U on the left and on the right by two different unitary matrices constant in time, and the Lagrangian remains invariant. You see that whether you put it here or there, they cancel each other, the trace would bring them together. So this has a double, it's a UN cross UN invariance. And these invariances correspond to some conserved quantities. These are classical conserved quantities because of these invariances that will also be the generators of these transformations. And they are conserved because they are essentially equivalent to the equations of motion. Now, the unitary conjugation of this matrix that would leave the eigenvalues invariant, which is the one that we want to gauge, if you wish, would correspond to choosing V equal W, so this becomes VU W minus 1, and that corresponds to the generator of the conserved quantity being simply the sum of those two. It's generated by the sum of those two. And that sum, if you see, it's simply the commutator of U and U minus 1. Now we can do our standard tricks. I will not repeat this text. What did we do for the Hermitian matrix model? We parameterized the matrix in terms of its eigenvalues and the diagonalizer unitary conjugation. That's what we do here. It's just that these eigenvalues are all phases. You plug this form in the action, you crank it, you work it through, and lo and behold, that's what you get for the Lagrangian, eventually for the Hamiltonian, because in this case, Lagrangian and Hamiltonian are equal to each other. There is no potential. And this K is essentially J but unitary conjugated with this V, as exactly as in the unitary, in the Hermitian matrix model. What is this? This looks like the Sutherland model if only these things here were a constant. It's the 1 over a sine square potential. This K, as I state, is the unitary conjugation of J with respect to the diagonalizer, and it is not a constant of motion anymore. J is constant, but this V is time dependent, so this K is dynamical. Yes? Yes. Then it's still an invariance of the model, but it doesn't leave the eigenvalues invariant. It would act on the model, it would change the matrix, and it will also change its eigenvalues. If you multiply, say, where am I here? If you multiply, say, if you put W equal 1, and if you only do this, of course you change the eigenvalues, right? So it's a symmetry of the full model, but it also shuffles or changes the particles. We're not interested in that. We only want to gauge, does this work? We only want to gauge the unitary conjugations that leave the eigenvalues invariant. Does this answer your question? So let's go quickly through the steps. If you choose, again, if you choose J equals 0, which means K equals 0, then there is no interaction and you get free particles on the circle. Classically, if you choose J of the Calogero type, which is of this form, then exactly the same analysis as we did for the Hermitian matrix model implies this relation. So when you put it there, you recover the Sutherland model because this Kij, Kji becomes simply that constant. So everything works as before. And what would be the integrals of motion? Well, they are the traces either of L or of R, or of R. L and R, I remind you, are these two. You can call it the left momentum or the right momentum matrix. Their traces are actually equal, so up to a sign. So trace of L to the n and trace of minus R to the n are equal. So you recover one tower of quantities that are trivially conserved. You can find the solution of the model because when you have the equation that u minus dot u minus 1 u dot equal a constant u is necessarily of this form, you can immediately integrate that equation. This B and C has to satisfy a constraint that they have to give you J in this form. And exactly as in the Hermitian model, you can find the solution by diagonalizing one of them. Everything works the same. Actually, this model contains the Hermitian matrix model if you rescale your coordinates, if you say that x is now x over a would be the radius, the periodicity of my space in units of 2 pi, and then you take the limit a going to, that's wrong again, a going to infinity. You want the periodicity to go to infinity. Then you recover the Calogero system only free because there's no potential. Okay, let's quantize it. Again, many things are similar as before. You can define the canonical momentum of u, but this is what it turns out to be. This is a rather, although it satisfies this nice canonical commutation relation, it's a rather unpleasant matrix because it's neither unitary nor Hermitian. It's best to multiply it to the left or to the right with a u, in which case you get these L's. And using the standard commutation relation, you find that, surprise, surprise, the L and the R matrices that you define like that satisfy the same algebras as the L and R that I defined before. So they are UN algebras. They commute with each other. They generate different transformations, so they commute with each other. So everything is as before, where now these L's are momenta matrices, left and right momenta matrices, not left and right Hamiltonian matrices. In fact, I1, which is the trace of either of these matrices, is simply the total momentum. I2 would be the total energy, and the higher INs are higher integrals of motion. How do you construct the states? Again, I guess I will just skip all details. I don't want to spend too much time. Let me actually, you can read it, and it's nice, but let me state the final thing. U the fundamental variable of, let's quantize, first of all, the system in the U representation. That means you have wave functions of U. Your wave functions, your states become functions of U. And you would integrate these states, or the absolute values, with the invariant measure in U, which we call the Haar measure. U is a UN matrix, so it belongs to the UN group. So it has representations. Pick any irreducible representation of that group. So call these matrices R. So R, with alpha, beta being the matrix indices of R, is a representation matrix for that group. And represent your dynamical variable U, the matrix U, in that representation. So this R alpha beta, let me go to the final thing here. This would be your wave function, this R alpha beta as a function of U, these matrix elements as a function of U. You proclaim that to be your wave function. Why? Because it turns out that this wave function acted upon with the quadratic Casimir of L, or equivalent the quadratic Casimir of right with trace of L square, it is an eigenstate with eigenvalue, the quadratic Casimir for that representation. But the quadratic Casimir of L, trace of L square or R square, is the Hamiltonian. So these are all energy eigenstates. So this is the statement here. So we have identified the energy eigenstates of the full unitary matrix model, regardless of anything else. All these matrix elements for all irreducible representations together are your energy eigenstates. And it's actually a complete set by the standard completeness argument of representations. You can represent any function on the group space, UN, if you consider all the matrix elements of all irreducible representations. So we have solved the problem. And we immediately know that the energies will be half, actually, because of the 1/2 in the Hamiltonian, of the quadratic Casimirs of UN. Because each such state is degenerate, all elements, each and every element represents a state with the same energy, we realize that this energy spectrum is highly degenerate. In fact, if that has dimensionality dr, the number of functions here is dr squared, right? It's a Hermitian dr times dr matrix. So we obtain a spectrum that consists of these quadratic Casimirs with various degeneracies, dr squared. Now, of course, that's not interesting because, again, we have to reduce to the sector with a fixed angular momentum. So we need to do that. Again, this can be done rather easily. These indices here of that representation, alpha, the index alpha and the index beta, transform in the fundamental of L, this alpha, and the anti-fundamental of R, this beta. It's kind of natural and obvious, and you can show it, but I just state it. Oh, good. So these states taken together, these dr square states, are transforming in the representation R cross R bar, R here, R bar there. And that is the representation of J, because the sum of left plus right is J, so we know what representations are here. It's R cross R bar. We need to take this representation, which is not irreducible, it's a direct product of R with its conjugate, and decompose it into irreducible components. Same constraints as before, because it is of this form, it will have the same zero CN chart, so exactly the same types of representations as before. So in principle, we need to take this R and apply the Klebs procedure, isolate out of these states the one that transforms in some irreducible component of little r, of J, and those will represent our physical states. What is the spectrum of that model? Well, it's actually just the quadratic Casimirs of the UN group. Now, how many of you are familiar with the fact that the quadratic Casimirs of the UN group, if you look at all representations, is nothing but the energies of n free fermions on a circle. It's a cute fact that can actually be proven. It was known, I forget who was the first guy who noticed it, but if you take your UN group and look at your quadratic Casimirs and you write them in terms of the Young tableau lengths of the representation, and you do a transformation, you define a new variable, lo and behold, that becomes the sum of the squares of numbers that can be interpreted, of integers that can be interpreted as the momenta of particles on a unit circle, but these numbers have to be different than each other, so it's a spectrum of free fermions. So we already know that the full matrix model will have the spectrum of free fermions. Only the degeneracies will change. Before we go into that, let's actually do what we didn't do in the Hermitian matrix model, we saved it for here, and derive the quantum mechanical particle model. Remember that classically we found that the Hamiltonian reduces to this value where this E0 could be some kind of constant due to reorderings. But this is essentially the classical function, where now these P's in this case become quantum mechanical operators. P is the momentum corresponding to particle I, and K are the operators corresponding to this angular momentum matrix J, unitary conjugated. So to extend this to the quantum mechanical domain is to determine the appropriate ordering of these operators, which will fix this constant, and take into account any measures involved in going from the unitary matrix to the eigenvalues in this case. And you may say, why do I have to do that? Well, think what happens when you have a problem, say, in Cartesian coordinates, the Schrödinger equation in Cartesian coordinates, and you need to go to polar coordinates. You could do it classically, and that would give you the momentum PR square plus the angular momentum L square over R. And then you would say, okay, good, now I can quantize that. PR, I will quantize it as d over minus IH bar d over dr, and LR accordingly, and L accordingly. Would that be the right thing to do? No. You would be missing quantum corrections. In fact, you would be missing, for instance, the fact that the wave function has to vanish at r equals 0 when you do it that way. The problem becomes even more noticeable when you are in 2 dimensions. In that case, if you do it naively, first classically, you go to polar coordinates and then quantize, or you first quantize in Cartesian coordinates and then you go to polar coordinates, the 2 results differ by a finite dynamical thing, which is actually minus, lo and behold, minus 1/4, 1 over 4 r squared. You have an extra contribution to the centrifugal potential, which is purely due to quantum ordering corrections, or it can be considered to come from the measure. So I can do all that here. I can start from unitary matrix, which has this kind of measure, and transform this measure. This is like the kinetic term, right? So this is like the length element on the group in terms of eigenvalues in angular degrees of freedom. And you see that this thing diagonalizes. You have a sum over dxi squared, which is flat, plus a sum of these matrix elements of v minus 1 dv with factors of dxi. So the volume factor will be 1 out of here dxi times the product of these matrix elements, but with these factors appearing. And these factors, when you multiply for all ij, give you the famous Vandermonde determinant. So this result here, that the invariant volume element in the unitary space U is the flat volume element on the space of eigenvalues times the invariant volume element in this unitary matrix U that diagonalizes it times this Vandermonde determinant square. This fact is embedded in this statement. Well, that tells you that because the measure contains this extra factor, you better multiply your wave function with the square root of that factor so that the measure would become flat in dx and dv, so that you wouldn't have that appearing. And only then you can have a nice Hermitian-looking operator in quantum mechanics. That's exactly what you do again when you quantize in spherical harmonics, you redefine your wave function as R times something else. And that other wave function satisfies a simple Schrödinger equation. Because I see that I'm running short of time, you do all that. This delta of x, actually, this product of signs is nothing but the ground state of n fermions, because you see this is fully antisymmetric. It can be expanded in plane waves, and it corresponds to the ground state of having n fermions in the momentum lattice that you get when you are on a circular periodic space. So it's a sign of the fermionization of the eigenvalues that we were talking about before. Then this K also, because it generates this transformation now, sorry, J generates this transformation, but U generates a transformation of the diagonalizer matrix like that, also generates a UN algebra. So K also satisfies a UN algebra. However, because this is the diagonalizer matrix, if you multiply it to the right by a diagonal matrix, that would go through the diagonal and would not change U. What I mean, you see what I mean, is this thing here. Where am I? This thing here. If you multiply V to the right with a diagonal matrix, that would come to the left in V minus 1, because its diagonal would commute through L. So changing V that way would not change U. So it's a redundancy of the parameterization in V, and that amounts to the fact that the generator of these diagonal transformations has to be identically zero on quantum states, which means that these diagonal elements of K have to be zero. Again, we saw this in the Hermitian matrix model in a different guise. K does not commute with the Hamiltonian, but this constraint does commute. So again, you can realize K is in a Jordan-Wigner construction. And look at the title of this transparency, Let There Be Spins, that will actually answer a question asked by Manas yesterday. What happens if you don't choose the simplest form for J, but if you choose a rank 2, rank 3 choice? That's what happens. This K can be realized in a Jordan-Wigner construction in terms of n-cube oscillators. These kind of auxiliary variables like we did before. So this K will now have this form. If you choose only one such set, we are back to the Calogero system. If you have many such sets, it corresponds to having realizations that correspond to higher rank. This constraint tells you that the total excitation number of these oscillators must be equal to L, acting on a physical state. And therefore, this coefficient that we had in the potential term linking two particles, which was Kij, Kji, if you put K in that form, it becomes like this. This L comes from the fact that this total number is L. And if you see this is a sum over M and N, K and J are fixed. Therefore, if you kind of separate this into something that refers to particle J and something that refers to particle K, you see that you have an operator A dagger M AN for particle J and an operator A dagger K AM for particle A dagger N AM for particle J. Okay, so this is what I was alluding to. For each particle, define this operator A dagger M AN, so it has indices Mn, but it refers to particle J minus the trace, essentially. These operators are actually realizations of SUQ, where Q now is how many of these harmonic oscillators I chose in this realization. So now I have endowed my particles with SUQ spin. Each of those operators belonging to particle J is an SQQ operator. And if you see what happens to that term, and you massage it like that using this, you see that it becomes this form. It's Sj.Sk. So this is the group invariant scalar product of the spins of particle I here and particle j plus a constant. And because of these constants here, that constant turns out to be like that. So you take this, you plug it in here, and that's now your Hamiltonian. That's not quite the Sutherland Hamiltonian because it contains a term here which is still dynamical. These spins are dynamical. These spins are a reshuffling of the degrees of freedom in K, and K was a dynamical matrix. So we have obtained a generalization of the Sutherland model where the particles have spin and their interactions contains ferromagnetic type interactions between the spins plus a constant. So for free, if you wish, from the matrix model, we obtained a spin generalization of our Sutherland model. Exactly the same thing would happen in the Calogero model. I just saved it to do it here, just to give the unitary model some meat. And notice that the overall coefficient in front of this potential is fixed. It's 1. You cannot put a number g here. That number, everything you have here is fixed by the matrix model, and that number is 1. And this number here is fixed by L, which is the representation of J that you chose. This has to do with your angular momentum sector, and Q, which is the particular realization for S's that you chose here. So let's see what happened. If you choose Q equal 1, that means SU1, it is like choosing no spins whatsoever. So this term becomes 0. L then necessarily becomes L squared because Q is 1. So this total term becomes L squared. That's the Sutherland model, the spinless Sutherland model. Q equal 1, SU1 means no spin whatsoever, and you recover your Sutherland model. However, if you so that's Q equal 1. If you choose any other Q, you get a model with genuinely new degrees of freedom. And that model is solvable because we solved it. The full matrix model is solved. And we also know the spectrum. Again, the basic idea is that you take the total spin S, which corresponds to K basically, but it would be the sum of all the spins of the particles, which is still a conserved quantity for the system. The total sum of the spins is invariant because of the mutual spin interactions. So you take that total spin and you decompose it into irreducibles of SUQ. This Young tableau will be some Young tableau in SUQ with up to Q rows because it's an SUQ Young tableau. You interpret that Young tableau as a Young tableau of SUN that fixes the representation of K and of J because K and J are unitarily related, so they belong to the same representation. So it tells you, you want to know the spectrum of your system, decompose of your spin Sutherland system, decompose into total spin sectors, see what representation of J they give you, go to the original matrix model and read off the spectrum, and that gives you the answer. It sounds convoluted, but it's not that hard. Let's do it for the two simplest cases. Free particles would mean L equals 0 effectively, so J equal K equals 0. No spill, no potential, free particles. So you can only choose fully symmetric representations there. If you ask what is the number of times that your irreducible representation R cross R bar is contained in this one, there's just a single time. So you get a free fermion spectrum in that case. Why free fermion? Because I argued that the spectrum, that the second Casimir of the group, which is the energy spectrum, is the spectrum of free fermions. And with degeneracies 1, you have exactly free fermions. The spinless Sutherland model corresponds to Q equal 1 at L different than 1. R now has to have a single row and boxes. And if you ask the question, if I have a representation R and a representation R bar and I cross them, what kind of R should that be to have this representation R? You see that the acceptable representations, there is only one of them, and the acceptable ones are such that each row has at least L boxes more than the next one. So the representations for this R, alpha, beta, that determine the spectrum are only of these terms. This one will have some length L1, this one, or call it N1, this some N2, and so on and so forth. And you must have N1 bigger than or equal than N2. We know that, plus L, and N2 bigger than or equal than N3, plus L, and so on and so forth. So this tells you that you have essentially the same spectrum as free fermions. If you didn't have that constraint, it would be just all the representations that give you free fermions. It's just that now this extra exclusion relation, when translated to the corresponding fermionic coordinates, these P's that translate the spectrum into fermions, that amounts to this relation. So for L equals 0, you would have all the representations, and that would be the standard fermionic selection rule, that each one must be strictly bigger than the next one, so bigger than equal than the next one plus 1. Now you have plus L. So these are particles with generalized statistics, again, super fermions with generalized statistics of order L plus 1, exactly as I showed you yesterday. We are done with the matrix model. Let's just recapitulate what we did. We found that the matrix model actually not only solves the problem, but it also allows for generalizations where the particles carry spin. Yeah.
Right?
Correct.
So did you speak about that? I mean,
I didn't. I did the spinization directly in the quantum case. For the classical model, it would be exactly the same. You wouldn't have this kind of extra shift L to L plus Q. It would be simply L squared. And this S would obey classical spin Poisson brackets. And that has a name, actually. It's called the Wojciechowski, somebody else's model.
so I should just think of it as classical particles with 1 over r square and just having this additional classical spin attached to each of them.
Exactly. They would have a classical SUQ spin, and these spins are dynamical because the Hamiltonian depends on them, and they have Poisson brackets with themselves, the classical version of the SUQ algebra. Absolutely. Right? Of course, realization of K in terms of Q bosonic oscillators is not the only thing that you could do. You could choose fermionic oscillators that would give you exactly the same thing, but with an opposite sign here. So you would go from a ferromagnetic to an antiferromagnetic interaction. You can play other tricks. You can realize that group in terms of one bosonic and one fermionic oscillator. That would still give you a model. What is that model? It's what was already known in the literature as the supersymmetric Calogero model. And you can do all kinds of other tricks. You can have spin that belongs to SUP/Q, some kind of supersymmetric generalization of SUP, and so on and so forth. Finally, you can choose other types of matrices. We chose Hermitian and unitary. There are other natural choices. You could choose positive definite matrices. That means the matrix, the space of Hermitian matrices with a constant negative curvature, the matrices that are exponentials, real exponentials of Hermitian matrices, that would give rise to the hyperbolic Calogero model, which you can also obtain through analytic continuation of everything we've done here. So, farewell to matrices. Let's count our blessings or our gifts that we received from the matrix model. It augmented permutation particle into a continuous symmetry, allowing us to define statistics, in quotation marks, through irreducible representations of SUN. So all these quantizations, in some sense, correspond to particles with generalized statistics, but that costed us a quantization of the Calogero parameter into an integer, actually an integer plus 1, 1, 2, 3, etc. You could say that the realizations with spin correspond to some kind of non-abelian statistics of the particles, where the non-abelian statistics manifests in these spin degrees of freedom. And all these systems can explicitly be solved through the matrix model, quantum mechanically and classically. What it did not provide us was a realization of these models for fractional values of L. You could say, gee, I can analytically continue everything I found. Yeah, but it's not quite so right, because you always run the risk of running afoul of some condition that was specific to the matrix model and doesn't immediately generalize. You do not recover spin models where you have a control of that coefficient here. Remember that this coefficient has to be fixed to 1. These spins can be as large as you want, but the coefficient here can be 1. And finally, the representations of these spins, which I didn't stress, I guess, have to be fully symmetric. They are realized in terms of oscillators, so they are SU2 spins either in the fundamental or the doubly symmetric, triply symmetric, and so on. So you get higher spins, but all of them in the symmetric representation. So those things are a little bit annoying, the integrality of L and the fact that these spin Calogero systems, as we call them, have no control of the coupling strength. We would like to be able to introduce an arbitrary coupling strength for reasons that I will hopefully describe in the sequel, so we need a new approach. Any questions to that point? Yes.
Suppose you replace the SUN group by a symplectic group, do you get some other models?
I'm sorry?
Replace the SUN group or the UN group by a symplectic group of appropriate dimension. What kind of models do you get?
Yes. You obtain what sometimes are called reflection symmetric types of Calogero models. And I didn't want to do that because I planned to talk about these models and lots of other reductions in part of my lectures called foldings of this model. I don't know if I will have time the way things are going, but I can either tell you in private or very briefly mention it. Yes, any kind of group that you can think, plug it there, do your tricks, give you a Calogero-like system. So I'm going to talk about the operator formalism for these models. We go back to the particle system. No matrices to talk about. We go back to the quantum mechanical particle system. We have coordinates x and canonical momenta p. And we define there the particle permutation operators, and so that I don't confuse them with momenta, I call them capital M. So capital M is the operator permuting particles I and J. Of course, they obey the standard symmetric group relations. They are Hermitian. They square to 1 effectively. They square to 1, and so on and so forth. I will define as one particle operators any operator in the system that has a particle index which is permuted by the action of M, as you would expect for an operator belonging to particle I. And you would say, aren't these single particle operators that refer to a single particle? No, I can create operators that involve all particles, but if they have this property, I will simply call them one particle operators. Yes. All right. So without further ado, I will define my basic tool here. This is a generalization of the momentum of particle J. Pi J is Pj plus an extra term, and this extra term involves a function of the difference of the distance between particle J and particle K times the permutation operator of particles J and K summed over all other particles j, which I will write like that, suppressing this dependence. This is actually a one particle operator, although it involves all other particles. If you act on it with mij, it commutes exactly in that way. So it's a good operator to consider as a one particle operator belonging to particle j. Of course, I would like these new momenta that I define involving these exchange operators to be Hermitian, and that means that this function w that I will call the prepotential must satisfy this hermiticity condition. And I will define my free, in quotation marks, Hamiltonian to be simply the kinetic term built out of this generalized momenta pi. If you substitute the expression for these pi's into h and do the summation and massage it a little bit, you will see that the result will contain, of course, some of the ordinary momentum squared plus extra terms, and some of these extra terms will be linear in momentum. So it will look nothing like a regular Hamiltonian. And I don't like that. I would like to end up with a Hamiltonian that looks like a Hamiltonian of particles p squared plus something depending on coordinates. And for that to happen, that imposes an extra condition on that prepotential that it has to be an odd function, which also fixes it to be real because of the previous reality condition. Finally, I have to calculate the commutators of these pi's. The p is the momenta commute. What about these pi's? You crank through the calculation, and you see that it's a term that depends entirely of a relation between a function wijk, which is given by this combination between the prepotentials. Remember, this is w of xi minus xj, w of xj minus xk, etc. So it's this function times mijk minus mjki. Mijk is the cyclic permutation of three particles, and this is again the cyclic permutation in the opposite way. And this is the Hermitian conjugate of that. So this is an anti-Hermitian operator, as it should be. Well, this means that in general, these pi's do not commute. So although this is a Hamiltonian that looks simple, pi is non-commuting tells me that its properties are not going to be very easy. I would like this commutator to be ideally zero, or at least as simple as possible, so that I can work with it and prove integrability of this Hamiltonian. So I will ask for the right-hand side term here, this w, to be either zero or a constant, which is the most general case. This means that this function that I define here, which takes this form, x is the distance between a particle I and j, y between j and k, and this would be the distance between I and k. This function must satisfy this functional relation. This we can solve, it's actually solvable. And for zero, we find that, lo and behold, w must be L over x. And for other constant values, either negative or positive, this w should be either the cotangent or the hyperbolic cotangent. So for these terms, for each one of these cases, you get a form of this generalized momenta. So for the right-hand side being zero, the generalized momentum is p plus this particular combination of the inverse distances of particles times this constant I times the permutation operators. This, by the way, are referred to in the literature as Dunkel operators. They were introduced by a mathematician, Dunkel, looking for symmetric polynomials and groups, etc. And they are exactly of that form. The nice thing about these operators is that for this choice, they commute, because remember, this w was the right-hand side of the commutator of pj on pk. So, now, in one sweep, we have something nice. Our Hamiltonian is sum of the squares of these pi's, and the pi's commute. So this is an immediately integrable system. The pi's commute, so if I want to have permutation invariant quantities, I can sum powers of these pi's, and those will be also commuting with the Hamiltonian because everything commutes. But these would be integrals of motion. And those integrals of motion would be integrals of this Hamiltonian that I have here. Now, notice that this Hamiltonian is very close to the Calogero Hamiltonian without an external potential, except that the strength of the inverse square interaction contains an exchange operator. We will call this the exchange Calogero model. It's very close and can be made to be identical to the Calogero model by assuming that now I quantize my particles as bosons or fermions, and by that I simply mean that I consider only symmetric or antisymmetric wave functions. On such wave functions, the action of these operators will be either +1 for bosons or -1 for fermions. So this would become L times L minus 1 or L times L plus 1. These quantities, because they commute with the total permutation, have a closed action on fully symmetric bosonic or antisymmetric fermionic states. So these quantities projected on such states would give me corresponding conserved quantities. These quantities commute, and by the fact that these are also local in the coordinates, you can show that their projection of these symmetric or antisymmetric states will also commute. You need an extra step here, but I won't insist on it. So in one sweep and without any effort other than the effort of devising this and proving the fact that these quantities commute in this particular case, we have proved the integrability of the Calogero model in the quantum Calogero model in one sweep. There you go. We can go further. We can consider the Calogero model with an external potential, use these pi's as your momenta, and construct ladder operators for a harmonic oscillator P minus I omega x and P plus I omega x for each particle. The pi's commute. The pi's and the x's now do not quite commute in the old way. There is an extra thing. So when you try to commute the a's and the aj's, you find that all the a's commute among each other, that's fine. And of course they are Hermitian conjugates, but the a and the aj dagger do not commute to delta ij anymore. If I is equal to j, they commute to this quantity, and if I is not equal to j, they still have a non-zero commutator. So it looks like it's not quite as nice as before. Now, the Hamiltonian of the system, this Hamiltonian that I showed you before, plus a harmonic term, 1/2 omega square xi squared, this one that I show you here, can actually be written this way. You just put that in, you work it out, so you the symmetrized product of AI and A dagger gives you this Hamiltonian. So you take this Hamiltonian now and you commute it with AI and AI dagger using these commutational relations. You see that these extra terms actually drop once you form this bilinear and you symmetrize it, and you have these commutational relations, which tell you that each one of these AI is an annihilation operator for the full Hamiltonian, and AI dagger a creation for this Hamiltonian. So we are basically done. Because if we can find the ground state of this Hamiltonian, we can create all these states by acting with these creation or annihilation operators. And we know that these states will have energies that will be multiples of this energy omega. So that's actually how the Hamiltonian right, so let's go quickly. You can easily show that if you take your Hamiltonian and act on a bosonic state, there is actually a state which is symmetric and is annihilated by all the AIs. So this is definitely the ground state because your full Hamiltonian is like that. On a bosonic state, this becomes just a C number. So it's a question of what happens here. So this state is annihilated by all the AI. So this is the ground state. Act on this ground state with your AI daggers, you create all the excited states. For fermionic states, again, you can find a ground state which is annihilated by AI, but it has this form. So you see that for fermionic states, this L better be negative, while for bosonic states, this L better be positive. Remember that L enters this way, So positive or negative doesn't really matter for this part, just matters for this sign here, if it's positive or negative, and that's what differs between fermions and bosons. So you may ask, what happens in the wrong combination? What if you have bosons with a negative L or fermions with a positive L? It's a little bit more complicated. It turns out that there is no state which is annihilated by all AI, but there is a state which is annihilated by all symmetric polynomials of AI, which is what you really want, because you are not really interested in single particle operators. You're interested in permutation symmetric operators, which are the true operators of indistinguishable particles. So you can define such states, and everything works fine. A basis for the excited states for indistinguishable particles is any symmetric combination of creation operators, which can be this and all powers. So the spectrum has it, and have I written the state at some point? Oh, okay, I guess I could write the state to be the ground state acted upon with an arbitrary sequence of such operators, as many of them as you want, and you get the spectrum of free fermions, but with this extra shift, which is now the ground state, which is exactly what we covered before in the matrix model. But now this L does not need to be an integer. So now we have the spectrum for the full Calogero model. Integrability can be shown. Remember that the pi's commute, but here we have also the harmonic potential, so we should really be working with these operators. And just as before, we can form these single particle Hamiltonians, call them AI dagger, AI, little hi. And these hi obey this kind of algebra. It is linear, but it also involves this permutation operator. And with some work, it's not entirely trivial, but requires some work, you can show that these powers, sums of powers of in, commute with each other. So these are integrals of motion. N equal 1 would give you actually the Hamiltonian. Higher n's give you higher conserved quantities. Similar results hold for this H tilde. This would correspond to the left, and this to the right. Single particle Hamiltonian, and these i's are related through each other. Let's go to the other cases, to the case that the pi's don't commute, but commute to a constant times this triple permutation operator. In that case, the Hamiltonian becomes like that. When you plug pi's that I remind you in that case, oh, there they are. In that case, W is like this, so the pi's would be L cotangent X times Mij. I don't know why I didn't write it. Oh, they are here actually. I don't know why I didn't write it when I did write it actually. Okay, and they commute like that. The Hamiltonian obtains this form. No surprise, it's the exchange Sutherland Hamiltonian, Sutherland with this M appearing there, plus a constant, although this constant still depends on some pure permutation operators. So when you act again on purely bosonic or fermionic states, this becomes a constant, this becomes a constant, so you recover the standard Sutherland model. The ground state of this model is the state on which all these pi i's would be 0, because remember, your Hamiltonian is the sum of pi I squares. It became like that when we wrote it explicitly, but the sum of pi I square. So if there is a state which is annihilated by all the pi I, that is definitely the ground state, and this state has this property, again, for bosonic states. And then you see that L has to be positive. And here, I should have negative L, but that's okay. So that's an example, again, minus L, so it's acceptable for both, for positive L, Fermi negative L. For both cases, the triple permutation indexes, particle operator is 1. 3 particles. When you cyclically permute 3 particles, you get always +1. So this ground state energy assumes this form, which is exactly the ground state energy of n free fermions on this circle. That's what you get actually, times L squared. And to prove the integrability of the model and eventually solve it, you have to find integrals. The integrals will be sums of powers of the momenta. I define these new slightly modified pi's that will now have the property that their commutation relations are a little bit different, but it allows you to do it. Let's skip the details. And so you prove that the model is integrable. And without further ado, you can go to the hyperbolic case. You get the sine square, exactly the same with a minus sign in the commutator. Everything works. Or you could take the analytic continuation of x to ix, and everything would work just fine. So everything that I showed you here works directly and only for the quantum case. I can introduce spin here as well. Let's do it quickly. Assume that the particles carry a number q of discrete internal states. Remember, I assumed at some point that my particles are indistinguishable, but I didn't have to. The model that I obtained explicitly containing, let me flash just that once more. The model that I obtained, too far. This one, the Hamiltonian that I obtained, and the final Hamiltonian here, contains this term. This Mij is the permutation of particles. It doesn't have to act on a particle symmetric state. It can act on a state of arbitrary symmetry. It will give you something. The particles could be fully distinguishable. So this full distinguishability of the particles, you can trade for particles having internal degrees of freedom. You could say that your particles now come in Q colors, if you if you wish, that those colors do not participate in the dynamics. It's just that the wave function, the Hamiltonian will exchange particles, and therefore it will exchange these colors. Define as sigma ij the operator that exchanges the internal states of particles I and j, and therefore the total permutation operator exchanging both kinematical degrees of freedom, positions and momenta, and internal degrees of freedom is the product of Mij and times sigma ij. Now, quantize your system as bosons or fermions in terms of the full particle permutation. You permute particles with their internal quantum numbers, and you impose a condition that the wave function be periodic or anti-periodic, bosonic or fermionic. Because of this property, that means that when you act on such a wave function with the position exchange operators, you get plus or minus the action of the color or spin, if you wish, exchange operator. Therefore, your Hamiltonian acting on such states becomes the same Hamiltonian, but with m here substituted by plus or minus, with the minus sign minus or plus sigma ij. So it became a Hamiltonian that involves interactions of the particles' internal degrees of freedom. This operator here exchanges the spins of the particles. I think I should conclude, but let me finish with this here. Do we know of an operator that exchanges the spins of particles? It is actually this. If S's are spin operators in the fundamental representation for particle I and particle J, this product plus a constant is the operator that exchanges the spins of these particles. So if you plug that expression into the Hamiltonian, you get a term which is L times L plus this operation with plus or minus. This plus or minus has to do this plus or minus here, plus constants. So what is this? It's exactly the model that we had before. It's the Calogero or Sutherland model with spin interactions here. But these spin interactions, again, can be either ferromagnetic or antiferromagnetic. They have an extra constant, but the overall coefficient now can be arbitrary. So that's nice, because now I have a spin model where the strength of the interaction is arbitrary and I can take it to be whatever I want at will. So this is in some sense better than what I got in the matrix model. The one thing in which it's not better is that these spins must necessarily be in the fundamental of SUQ. In matrix models, these spins could be in any symmetric representation of SU2. So if we have SUQ, so if we have, say, SU2 spins, regular spins, they could be spin half, spin 1, spin 3 halves, spin 4 halves, any spin. While in this case, they would necessarily have to be spin half, no higher spin. But the coefficient can be arbitrary. So that's where we will have to leave it. We will briefly talk about the spectrum of the spin Calogero model in the next lecture, and then skip forward to talk about the hydrodynamics of this system and make contact with some stuff that was described to you previously, in particular by Sasha Abanov. Okay, that will be it for today. And hopefully I'll do it in a better voice since it will be on Monday.
Questions, comments?
Normally, when you have a spin system, you can trade the spin permutation operator for the coordinate permutation operator. But in this case, it does not really make sense because there is no process that permutes the coordinate.
There's no what?
No process that permutes the coordinate because the particles are impenetrable.
No.
So, although mathematically makes sense, physically is not allowed, or is?
I will give you the short answer that this is not the case because the Hamiltonian explicitly involves, let me go again to the basic, oh, there it is. The Hamiltonian explicitly involves particle exchange operators. So it's not impenetrable anymore because it has a part that teleports particles. And in fact, kind of giving away a small punchline of the next lecture, the Hamiltonian with this interaction, not only the particles are penetrable, but they are fully penetrable. The particles completely go through each other. There is no backscattering. So it's the exact opposite end, all because of this term over here. That's a good question. Thank you.
Any other questions? All right. May I ask you, is there any way, is there any ideas how to generalize this construction for the elliptic Calogero?
Right. The elliptic model is a challenge in general for everything. I will admit that I don't know the literature on the exchange formulation for elliptic models of the last several years. Not to my knowledge, but I wouldn't be surprised if it has been done. Let me check and I will come back to you. Oh, also I wanted, if you permit, Chair, to respond to a question by Fabian Essler yesterday. Fabian, it was not a stupid question. It was a, can you not spoil it for me and let me answer? So I will. So I mentioned that the 1 over x squared potential is the borderline potential as far as the long distance behavior, not short distance, but long distance behavior of the potential is concerned, for which a system, in one-dimensional system, has or has no phase transitions. If the potential falls off slower than 1 over x squared, the system has phase transitions. If it falls faster, it does not. And Fabian asked very reasonably, what kind of phase transitions can you have in one dimension? Now, there is indeed a kind of folk theorem that in one dimension you don't have phase transitions, but for particles this is only true if you have short distance interactions. If the interactions are long range, then you can have transitions. And in fact, it was Dyson, I think in 1968 or so, who showed it. He did it actually for a lattice gas, not particles, but it's exactly the same calculation, that if the particles interact with 1 over x to some power, and that power is less than 2, then the system will have a phase transition. If that power is more than 2, the system will not have phase transition. So that's another very special property of this 1 over x squared system. system is exactly at the border between no and yes phase transitions. And thank you, Fabian, that you made me actually check, remind myself exactly what's going on.
Okay, so let's thank the speaker again.